Okay, so let's recall quickly what the QFT does. It takes every state of an orthonormal basis of an n-qubit system, which means a 2 to the n dimensional space, into a superposition of this form. This is, yeah, I have to keep checking my notation again. So this is k going from 0 to capital N minus 1. So capital N is 2 to the n, right? 1 over square root capital N e to the 2 pi I j k by n k, and this is what we called as j tilde, right? Okay, so what we saw in the last lecture, and those of you who couldn't make it, I hope you've seen the recording by now. The recording has been uploaded. What we saw last time is that this superposition can actually be broken down into a very nice product form of this form. So this j tilde, which is the Fourier transformed state corresponding to ket j, actually can be written as a tensor product of this form. So in each qubit, it is some non-trivial phase superposition of this form. So this is e to the 2 pi I. So we'll explain this notation again. Point Jn, this is ket 1, tensor 2 pi I Jn minus 1 Jn, and so on and so forth, all the way up to 2 pi I. Now this is this is inverse powers of 2, right? That's what we saw last time. So this is J1, J2, etc., all the way up to Jn, ket 1, right? And this whole thing with the normalization 2 to the n by 2, right? So what does this notation mean? So point Jn basically means, so let me write out a general, so what does this decimal notation mean? So this is actually not decimal, this is basically binary fraction. So this is so these are all to be expanded now in inverse powers of 2 as opposed to powers of 2, right? So recall that j, when I say that j is associated with j1, j2, etc., jn, right? That's what the j1 to jn are here. Then this actually is an expansion of the form sum over L going from 1 to n jl 2 to the n minus L, right? And now when I do this notation, point j1, j2, etc., jn, then this basically you have, instead of associating a power of 2, so here with j1 you're associating the power 2 to the n minus 1. With jn you're associating the power 2 to the 0, right? So this is going to be the other way around, where now with j1 you're going to associate 2 to the minus 1. With j2 you're going to associate 2 to the minus 2, and with jn you're going to associate 2 to the minus n, right? So this is now a sum of the form I going from 1 to n, I shouldn't say I again, maybe L going from 1 to n, jl e to the, 2 to the minus L, right? Okay, so this is what we mean by, this is the binary expansion for j, the binary representation, and this is now this is how the fractional powers are represented. So you notice that, and this was sort of proved or shown last time, right? That this is what the Fourier transform does. In every qubit, this is, it is going to introduce this non-trivial superposition with this phase. So the key is to basically get these phases out, right? So now if I imagine, so I want to now get a circuit for QFT. So what does that entail? So there are n input registers, and let's say that these registers correspond to J1, J2, etc., Jn. Now, so let's say that this is the QFT circuit box. We'll have to see what's inside it. But note that this first output register should now be in what state? This should now be in 0 plus e to the 2 pi I jn by 2, right? That's what this is now, remember, right? This is 0.jn means this is jn by 2, right? Get 1. That is what this output register should be in. So you notice that this phase, so okay, by square root of 2, right, for normalization. So how would you realize this superposition? This requires what kind of gate?
This is equal, sort of equal superposition. So Hadamard gate would be involved.
The Hadamard gate will only get you to 0 plus 1 by root 2 all the time, or 0 minus 1 by root 2 all the time, right? But this Jn, of course, the Jn is either 0 or 1. You are right. Right? So if it is 0, then what is this? This is 0 plus 1 by root 2. If Jn is 1, then this is 0 minus 1 by root 2. But now, okay, good. So this is a Hadamard, but there's something that decides whether this becomes a 0 plus 1 by root 2 or a 0 minus 1 by root 2. And that something is not J1, right? What is that something that decides what phase this should be?
Jn.
It's actually Jn, exactly. So this somehow has to be a Hadamard on Jn, right? So what one could do is think of putting a Hadamard here with the where the input is now ket Jn, right? So these are all, of course, ket J1, ket J2, etc., where J1, J2 are all 0, 1. But that now becomes your most and least significant qubits in some sense are swapped, right? So indeed you put a Hadamard here, but that Hadamard in the end will give you a state which has to then be swapped with this state, right? So this is the first thing you observe, that this is like a conditioning in some sense. So this is now conditioned on the Jn rather than the J1 here, right? But this is the first qubit of the output state. So this is working in the inverse order, right? So there is some kind of swapping that's going on between the input and the output. And so indeed, you will realize that the circuit involves a bunch of swap gates. So good, this was the first qubit. Let's now look at the second qubit. So let me keep this. So I'm just trying to motivate what the circuit, why you get the kind of circuit that I'm just going to draw. So let's now look at the second output qubit. The second output qubit, so let's leave the normalizations out. It's understood that this is all, so let me just write here that this is a Hadamard, right? Okay. Now the second one has a phase of what? This is now Jn minus 1 Jn, right? So this is Jn minus 1 by 2 plus, so the phase itself is now like this. There is 2 pi I Jn minus 1 by 2 plus Jn by 4, right? Now what happens? There is a phase coming in exactly like a Hadamard, but that is now associated with Jn minus 1. But on top of that, there is one more phase, which is a Jn phase. And that now is what? I pi by 2, right? If Jn is 1, this has to become, this is to actually become an I, right? So there has to be now, what are the gates that should be involved here? So you realize that just Hadamard won't do, correct? So this part can come from the Hadamard. Very good. So Rajesh is saying that you need controlled phase gates. Exactly. So first of all, you realize that you need a phase gate. Once you have a bit by 4, right? So then the phase becomes either 0 or I pi by 2. And the 0 or I pi by 2 can be realized by a phase gate. But of course, now this has to be conditioned on the Jn, right? So you can think of this as a controlled phase gate. So what you can do is think of the n minus 1th qubit here, do a Hadamard, but that is not sufficient. you have to condition also on the Jn value, and what you must have is some kind of controlled S gate conditioned on the nth qubit value, and not after the Hadamard, please, but before the Hadamard, right? So this is what you need. There has to be a controlled S gate here, right? This is what I'm drawing here. And that is to be controlled by the Jn qubit. So the Jn minus 1 has a phase which depends on both Jn minus 1 and the Jn. But note that finally this is not going to be the state of the n minus 1th output qubit. In fact, it is going to be the state of the second output. So again, there is a swap involved. Okay. So putting all this together and realizing that with every successive power of 2, so now when I have a Jn by 8, right? That's the next thing. I have 2 cube. So I have 2 pi I Jn by 8. What gate is that? Do we have a gate in the gate set for this?
T gate.
Exactly. So this is going to be the T gate. So this will require the so-called T gate, which now has a phase of pi by 4, right? There is 1, 0, 0 e to the I pi by 4. So what you realize is now you're going through a sequence of phase gates, right? So let's define this entire sequence of phase gates like this. So I'm going to say Rk is the gate 1, 0, 0 e to the 2 pi I by 2 to the k. Let me write this bigger. Okay, I hope this is clear. So now we've just identified some of the gates in this sequence. So what is R0, if you will? What is R0?
Identity.
Sorry?
Identity.
Identity. What is R1?
Z.
ZK.
What is R2? S. R3, T, etc., etc. So we haven't named the gates beyond this, right? But you can see that this is the sequence that we have, right? And what is more, now we have to implement these phase gates in a controlled fashion, because the phase that one qubit gets, in fact, you will see that now the second qubit here has an output which is conditioned on 2 of the input qubits. The third one is conditioned on 3 of the input qubits, and obviously the last one is conditioned on all n minus 1 of the input qubits, right? So what the Hadamard gate allows you to do is to do this Z kind of phase, which is a plus or minus 1. Instead of a control Z, you essentially do a Hadamard, right? Because it's conditioned on the same qubit, right? But the rest of them have to be done in this controlled fashion. So let's draw the circuit now. So this is what the QFT circuit looks like. So I'm going to assume that now you have these boxes which are going to implement these different phase gates for you, right? We saw that, in the universal set itself, you have the, or at least I mentioned, I didn't prove this for you, but the universal set can be realized using the phase, the T gate, and the Hadamard. So you already have 3 gates which are part of the universal set, right? So the universal gate set, at least one universal set, had Hadamard S, T, and C0, right? So now what you will need is not just the C0, but a whole sequence of other controlled RK gates, right? So you have, so R1 is basically realized via Hadamard, because most this R1 comes conditioned on the same qubit. Depending on whether the input is 0 or 1, you have a phase of plus or minus, right? So you see that this basically takes care of R1, this takes care of R2, this takes care of R3, but then all the other gates, now you have to actually decompose them in terms of these universal gates, right? But we'll assume that such a decomposition of course exists, and we'll put a box for the different RKs, okay? So this is what I have, my input J1, right? And J2. So like I said, in the end, we'll do a bunch of swaps, but modulo the swaps, this is what we have. I first have a Hadamard, right? Because there is a phase that always comes from just that qubit itself. And then I have a controlled R2. I have a controlled R3, but now that is controlled on the next one, which is J3. Etc. all the way up to Rn minus 1, which is controlled by Jn minus 1. So you realize that before you do anything to the Jn minus 1 qubit, you better do all the controlled operations that need to be done. Because the controls are based on the input state, not on what happens after you do a Hadamard to this, right? So you better do all the controlled operations that are controlled on a particular qubit before you apply the transformation gates on that qubit itself. So that's why the first thing you're doing is on J1, controlled on all the other qubits, right? So this of course is the actually the state of the last output qubit, the nth output qubit. So you will of course do a swap in the end. So this takes care of the first qubit, right? So now nothing more needs to be done here, and this will give you the state 0 plus e to the 2 pi I 0.j1, j2, etc. all the way up to jn. This is the superposition that this is going to give you. Of course, with a 1 over square root 2 that comes naturally from the Hadamard already, right? So this box, whatever we've drawn so far, is basically the box for the nth output qubit, but that will be realized at the location of the first output qubit, right? And in the end, we will do a bunch of swaps. Similarly, the second qubit here again requires a sequence like this. It requires a Hadamard followed by an R2. It doesn't have, obviously, like I said, the R1 is what is realized by the Hadamard. This is an R2, but the R2 is now controlled on the J3, controlled by the J3. The R3 is controlled by the J4, etc. And again, all the way up to now only Rn minus 1, right? Which in fact is controlled by the last guy out here. So this box that we have drawn now, this sequence, this will give me the second from last. So the n minus 1th output state, right? But of course, it's here realized at the second qubit. So let me write this state also down. So 0 plus e to the 2 pi I, j1, etc., jn minus 1. No, I want to say j2 up to jn, sorry. Yeah, that's what the second last qubit will be, right? Okay, and then J3 and so on. But now I'm out of space to draw the very last one. So let me draw this box in a different color. Okay. So watch, let us look at the very last two qubits here, but these are the simplest things to draw. What should I do to the second last one? Hadamard and just a controlled R2. But a controlled R2 is nothing but an S, right? So let me stick to the notation and just say controlled R2. So this is all that needs to happen for this guy. And this will then be in the state 0 plus e to the 2 pi I jn minus 1. That's the one which is attached to the Hadamard, and then jn, right? So this guy will realize 0 plus e to the 2 pi I 0.jn minus 1 jn get 1. That is this box. And then there's the very last one. What should I do to the very last qubit?
Hadamard.
Just the Hadamard. Good, thank you. So this guy will of course be in the state 0.jn get 1. Of course, all of them come with a by root, right? But now you realize that you have realized the state of the first qubit at the nth qubit and so on and so forth. So this entire circuit is to be followed by a set of swap gates. And how many of them? How many swap gates do we need? Basically half the number, right? So it's n by 2 or n minus 1 by 2, right? So let's just say n by 2 swaps. Okay. So I hope this idea is clear. So this is what the QFT circuit looks like. So we can do a simple example circuit. The 2 qubit one is very trivial. So let's just do the 3 qubit QFT, for example, right? So the 3 qubit QFT circuit looks like this. There is J1, J2, J3. This one has Hadamard followed by S, right, which is controlled by the second qubit. And then there is a T controlled by the third qubit. The second guy again has a Hadamard followed by a control S, controlled by the last qubit now. The third guy simply has a Hadamard. And then what do I do in the end?
Swap.
Yeah, swap the first and the third. Right? So this is of course the notation for the swap, remember, right? And nothing needs to happen to the second qubit. That's already in the state it's supposed to be in, and that's it. So this entire thing is the QFT circuit. And this is 0 plus 2 pi I now after the swap, right? So then this just becomes, yes, 0.J3 get 1, right, by root 2. This one is J2, J3 get 1 by root 2. And this one will be in the state which is actually conditioned on all 3 bits. J1, J2, J3, 1, this whole thing by root. Okay, so I hope this idea is clear, right? We built up to it slowly. We first saw the product form, then we saw how to realize this product form simply using a sequence of rotation gates, right? and each of these gates are, the first 3 of them are already in our universal set, and the others are going to be basically simple decompositions in terms of these gates, right? So what is the total number of gates required? So what is the gate complexity of this circuit? So for every qubit, you need a certain number of rotation gates, these phase gates, right? So if for the first one, let's say, which, after, so let's assume you've done the swaps. So of course you have these n by 2 swaps. So let's put that. So you need n by 2 swap gates, right? And remember, the swap can be actually decomposed in terms of C naughts. The swap is a fully non-local 2-qubit gate, and it can be realized using a set of C naughts, right? So you have n by 2 swap gates plus how many of these phase gates? So this guy requires only 1, which is the Hadamard. The next guy requires 2, Hadamard plus the control S, all the way up to the nth qubit at the output requires how many? N. So that means a total of how many gates? N into n plus 1 by 2 plus n by 2, correct? So then this is a basically order n squared. So you need gates of order n squared, right? Whereas a classical Fourier transform, even the fast Fourier transform, requires order n 2 to the n gates. Okay, so this is the key improvement. So you have an exponential speed up in terms of the gate complexity. And gate complexity feeds both into circuit complexity and time complexity. So this is what you would call a polynomial scaling versus an exponential scaling. So even if you account for the fact that you have to decompose these single qubit gates further, they are only single qubit gates at the end of the day. And they are these simple phase gates, right? So using a combination of Z, S, and T, you should be able to realize these gates, right? So this is only polynomial scaling in the number of qubits, whereas this is an exponential scaling. The classical algorithm scales exponentially in the number of bits, right? Remember, little n is both the number of bits as well as the number of qubits that you have in the circuit. So that way you're comparing the same things, and you realize that the best classical algorithm still has an exponential scaling in terms of the number of qubits required, but this one scales only polynomial. Okay, all right, so that is nice. We have shown that it's possible to do this using just a circuit which involves just n squared gates, right? So now what can we do using this QFT? So that's what I'm going to discuss in the next 10 minutes or so. Questions? Okay, so although I have now sold you the quantum Fourier transform and I have said that this is exponential speed up and everything, but you should take this with a pinch of salt. The reason you should take this with a pinch of salt is because what is the QFT algorithm or the QFT circuit doing for you so far? If you give me an input state, right, which is now, of course, if I do this on one of the computational states, then I can do it by superposition, right? Everything is linear, so I can do this on an arbitrary state. So if you just look at the level of the computational basis states, what is it doing? This circuit is taking J. So I'm going to now use this notation. When I put a cross here, it means that there are multiple qubits here, right? So if this is an n qubit state, okay, I have this box which does QFT. It's very nice. This is an order n squared box, okay? And then there is an output, which is also an n qubit output, which is basically the J tilde. So do you see a contrast between this and the classical algorithm? What a classical Fourier transform algorithm will give you? Is there a difference? You see, the classical algorithm typically, what do you use the Fourier transform for? Those of you who've done signal processing and so on, what do you use the Fourier transform for?
Transform the input vector into like a frequency domain representation.
Correct. But what is the information you extract from it? You see, the information that you extract from it is actually the amplitudes. So what you need are actually the Fourier amplitudes, if you want to use the Fourier transform the way you use it for classical applications, right? So while this does the Fourier transformation for you, to get the amplitudes is still a hard problem, right? It doesn't tell you what the individual 2 pi I j k by n are, right? Because this is now some superposition of this form, right? It doesn't tell you what these amplitudes are. Those amplitudes are still hidden in superposition. And if you have to extract this information out, what do you need to do? You need to measure. So far, there's no measurement here, right? The QFT just did the Fourier transform. That's it. You apply this, the deterministic unitary transformation. No measurement so far. But if you want to extract these amplitudes out, then they are still hidden in the superposition. And for that, you still need measurement. And of course, you know, because we have discussed this ad nauseum, that a single measurement will not do, because on a single copy with a single measurement, you only get one instance of this distribution. In fact, you do this multiple times, you're only going to get the modulus of this, right? You're not even going to get to this. So this now requires actually not just measurement, it also requires some amount of interferometry. It requires some amount of interferometry if you actually want to extract these complex amplitudes out, right? But with measurement, you can get some handle on the statistics and on the modulus of this, right? Okay, so this is the caveat that you should keep in mind when, you know, it's true that it's great that the Fourier transform can be done quantumly with exponentially fewer resources. But in order to actually realize the kind of classical applications that we need, but we typically use the classical Fourier transform for, that still does not provide you that kind of scaling up of the resources, right? Because this only helps you just do the transformation. That's all. But what I will now show you is that this transformation in itself is useful. And the fact that it can be done exponentially fast leads to other payoffs, right? And the first application of this, so that's what I want to do next. The first application is something called phase estimation. Okay. This phase estimation is again a kind of it's a paradigm, right? In the sense it's a like we discussed, you know, Deutsch or Deutsch-Josa was a certain model of doing things, right? The phase estimation similarly is a basic ingredient again, right, of several other quantum tasks that can be done using this, right? So this is not per se an algorithm, but it is more what you can think of as a subroutine or a part of an algorithm, right, rather than an algorithm itself. So what is the task here? The task in phase estimation is given a unitary operator which has eigenvector v, sorry, ket u. So ket u is some eigenvector of this unitary operator. Then lambda, let's say sub u, is the eigenvalue of this. What do you know about the eigenvalue of a unitary operator?
They are pure phase.
Exactly. So they all have modulus 1. So they are pure phase. So this can be written as e to the 2 pi I phi ket u, where phi is just some real number between 0 and 1, right? So this phi is basically the phase associated with a particular eigenvector of a unitary operator with eigenvector u, right? And the task is to determine or estimate, since you cannot do this exactly typically, the task is to estimate phi. Okay, and what you're given, so what is available is, or at least in this circuit we will assume that we are given the state u. Okay, now note that I've not put any dimensions here. It's whatever the unitary operator could be some d cross d unitary. So this ket u could be some d-dimensional complex vector in some complex linear vector space, right? And you assume that you're given that somebody has prepared the state ket u and given it to you and said, now estimate phi. So on Thursday, we'll see where such a task actually comes, like, where does this, how does this actually help? But for now, for this circuit, we'll assume that you're given the state ket u, that you are capable of performing the operation u and powers of u. So your powers of the form u raised to some k. So, and this is what we are given. Okay, then can one do this phase estimation? It turns out that, again, classically you realize that this is a very hard problem, because you have to now determine to some precision some real between 0 to 1, right? So estimating the exact phase of an arbitrary unitary operator is typically a hard task, right? But now, using the Fourier transform, it turns out that this actually becomes an easy task. And in fact, the Fourier transform, just at the end, by measuring the output, you can extract out the a certain number of significant digits of this phase. Okay, so that's where even not having access to the Fourier amplitudes, but just being able to do the Fourier transform already helps you in estimating this phase. Okay, so I will now just show you the circuit and then we will discuss how this is useful. Okay, so let's assume, so I just want to check what is the situation with the number of participants that you can. Okay, it's the same 30 of you here. Okay, fine. I'm just seeing the new people, then I again make the announcement, but that's it. Okay, so it turns out that what we need to do for this is we have to have two sets of registers. Okay, there is one set. So let me just show you the circuit here. Next time we'll analyze how this circuit works. Okay. So this is how the phase estimation circuit works. You have upfront a bunch of ancilla-like qubits. Okay, these are actually basically the data qubits. They are the qubits in which you're going to get the information out, right? So let me then call them data qubits. So let me just say that there are T data qubits. Okay, and all of them are initialized to ket 0 at first, and then on all of them we do a Hadamard to begin with. So you will notice that this algorithm again has the smell and feel of a oracle kind of algorithm where there is a Hadamard tensor n that is performed at the beginning. Then what we will have is another set of registers. These are not the data registers, in the sense the output does not, you don't measure these, but this is what is given to us. This is the set of qubits which is already prepared in this ket U and given to us, right? And what we need to do next is a whole sequence of conditioned unitary operations. Remember, the unitary also is a D cross D, so it acts on all these U qubits at once, right? So we first simply do a controlled U, okay? On the last of the data qubits. On the second last data qubit, we will do a control U squared. Okay, and then so on and so forth. On the first one, we will do, so now of course note that nothing happens here, right? Ket U is an eigenstate. So U acting on ket U is only going to give you ket U, but it will give you ket U with an additional phase, right? So that's what we are going to estimate. So we keep doing this all the way up to the first one will obviously have a, so this is 2 squared, 2 cubed. So it's basically U to the powers of 2. And here you have U to the power of 2 to the T minus 1. And on the very first one, U raised to 2 power T. Sorry, not 2T, but 2 power T. Okay. So this now, so the last part of the circuit, basically I'll just complete this, and then like I said, we'll do the analysis next time. Just bear with me for a couple of more minutes. So what we will do here, it turns out, is actually an inverse Fourier transform. So this will be a QFT dagger, right? Because remember, that's a unitary circuit, so the dagger is the inverse. So this is an inverse Fourier transform followed by a measurement in the computational basis. And that's it. That gives you estimates the phase phi associated with this particular eigenstate U, which you have prepared this in, up to T decimal places of accuracy. Okay. So let me just complete. So this is the inverse Fourier transform. Okay. And then measure in the standard computational basis. What happens to these second set of qubits? So actually, maybe let me call these as the ancilla now. So these are probably like the ancilla, although they're prepared in a particular state now. What happens to them? Nothing. They all just continue to remain in ket U, right? But because of this controlled operation, after the Hadamard, you realize that this information has actually traveled up somehow. The phase information has actually percolated here. Okay. So this is sometimes called a phase kickback. Those of you who do these IBM tutorials and so on, I think this is what they refer to as a phase kickback, where the information has actually gone from the target to the control, right? Because these are your controls actually. The data qubits are the controls, but the information is actually propagated the other way around. Okay. And that is crucially because of this superposition that the Hadamard throws you in. Every one of these qubits is thrown into the superposition, and then the control happens, right? So that's what helps with this. Okay, let me stop here and we'll analyze this next time. I don't want to start analyzing this now. So let's just stop here. Okay. Questions?
Yes, ma'am. I have a question related to the Grover search algorithm.
Tell me.
So in that, the oracle that we have, we assume that every time we input some state to the oracle, it will tell us if it's the state that if it's a solution or not, right?
Yeah,
But
yeah,
suppose I'm looking for the minimum of a say list, suppose.
yeah.
Then how does the oracle know if the given element is the minimum by just looking at that element?
So you'll have to give some threshold value, right? You'll have to do this, you'll have to engineer the oracle cleverly, right? It's like the traveling salesman or something, right? So you want to know the shortest route, right? So you'll have to give some kind of minimum value based on your estimate of what should be like a threshold, right? And the oracle will have to check every time whether the length, it'll have to compute the length of the route and check whether that length is smaller than this threshold or greater, right? Of course, it may
Right.
turn out that you get no solutions, in which case it means you have set a very short length, so you have to increase your length. And then you may get too many solutions, in which case you have to run it again by reducing that threshold, right?
Oh, okay. So the idea is that the
Compare
oracle.
for, yeah,
Oh,
yeah. So the oracle is not going to do something global for you, right? Even in the Deutsche Josa, the oracle was not doing anything global. The global aspects come in the beginning and in the end. When you do the superposition into Hadamard and when you undo that superposition, or when you do what we can think of as some kind of interferometry with the Hadamards, right? So the global part comes outside the oracle. The oracle looks at each x, each state, and says whether it should get a phase of +1 or -1. That's all.
oh, okay, okay. And one more thing, in the Deutsch-Joseph algorithm, when we measure complexity, we said it requires only one query, right? So it's one O of one.
Correct. Yeah.
But the
Yeah.
thing is that if you want to implement the oracle, it's going to be 2 raised to n cross 2 raised to n oracle unitary, right?
Correct. Yeah.
So that means it's going to require, like we discussed a decomposition for these unitaries, right?
Yeah.
Which is
Yeah.
going to be quite large. So are we not counting that in this?
Yeah. So that's the point. When you say oracle complexity or query complexity, then you do not worry about how complex it is to actually implement the oracle, right? Now, even there, implementing the oracle is still a polynomial scaling, right? It will still only be polynomial, but no matter what it is, you do not consider that. You're only looking at query complexity,
Oh,
right?
okay. Right, right.
It's only from a query complexity point of view, it has an exponential speed up. Of course, now, today, what we have seen is actually truly a circuit complexity point of view, where Fourier transform actually has an exponential scaling, polynomial scaling in circuit complexity, whereas a classical is exponential scaling. So this, what we've discussed today, is truly circuit complexity, but oracle complexity is never about how complex is it to do the oracle. So even in Grover, that O is just something that's completely submerged inside. You may discuss the complexity of the rest of the stuff. Okay, you need so many Hadamards, you need so many you need so many gates to do this, inversion about the mean, or this selective phase operation and all of that stuff. But O itself, that oracle, is complete black box, right? You don't ask how many gates do I actually need to do this.
Right, right.
So actually, that's why in that exercise in the assignment, when you did the Deutsch Josa, you realize actually doing that 3-qubit Deutsch Josa requires so many gates. Of course it does. It's a fairly decent sized circuit, right? But no, you don't worry. Yeah, you only worry about how many times do I need to run that circuit, and that is exactly one time.
Okay, right.
It's a way of estimating complexity. Right?
But even then, like particularly for Grover search, the oracle is like, so like the implementation of the oracle is like pushing. You could say like you're pushing the difficulty under the rug in some sense, right? Because uh, knowing that, so the thing is that if I'm trying to search for something in a database where, so if there are like 5 entries and each entry has a particular property. So like I'm looking for say one in a list of say numbers, then I can just say if the given entry is one or not. that is easier. But if I have to say do something like comparison, so something like finding minimum or maximum or something that is relative to other entries, in that case, I'll have, so that is not easy to do, right?
Yeah, so the oracle, like I said, doesn't do the comparison. It only is, see, it's understood in something like Grover, typically the oracle is actually going to be something classical, right? In the kind of problem that was given to you for the Deutsch-Jozsa is a kind of manufactured problem, right? You were given some particular Boolean function and then you were asked to make an oracle from that and so on. In a Grover kind of situation, the oracle will typically solve something classical. It'll be like, is this number a factor of this or not? Right? Does this number divide the given number or not?
Right, right.
So that's a classical function. So the quantum is going to do it at least as fast as the classical. So although you're pushing that complexity under the rug, it's the same complexity that exists in the classical case also. From an ideal theory point of view, don't forget the fact that a quantum gate is maybe exponentially harder to realize physically than a classical gate at this point. Okay, so forget the implementation angle and forget decoherence and all of that stuff. But from a theory point of view, this black box is as complex, not any more complex than the classical black box.
Right, right.
But while I have to run the classical black box capital N number of times, I only have to run this black box square root N number of times. That is the speed up.
Oh, okay, okay. Now I understand.
Yeah, so whatever the classical query setting is, you compare it with the classical query setting. You don't compare it to a classical circuit model. That would be like comparing apples and oranges, obviously. Say that you have a classical black box which does this, and then you have a quantum black box. And the hypothesis is the quantum black box is as complex but no more complex than the classical black box. Then you ask, you compare the queries, right?
Okay, right.
Yeah.
Yeah, now I understand.
Okay, good. Yeah, hope that clarified. Okay, any other questions? All right, if not, we'll meet on Thursday. We'll discuss phase estimation and we'll see the next application, which is how this can help us to do factoring, right? And with that, we'll wrap up the course on Friday. And I'll send out a message on Moodle confirming that the NSEM will be on 21st November, Sunday, 2 p.m. to 8 p.m. Okay, see you all.